very warm welcome to this new course in NPTEL platform, the thermal physics. Now, during this course we will be learning thermodynamics, the classical thermodynamics, and also some parts related to kinetic theory of gas and the transport related phenomena. So, our journey will begin from the kinetic theory of gas and we will slowly go into the domain of classical thermodynamics. Now, it is a 30 hours course and you already have the books with the textbooks which are marked, which are suggested by me for this particular course, and at the same time any of these textbooks will work, and of course, I will give you regular problem sets, assignments, classroom problems, everything will be given. More than that, on top of that, we will also have a live discussion forum, at least 2 or 3 during this entire duration of the course, where you can ask question directly to me during the video conferencing session, and of course, you have the regular discussion forum where you can post your questions, post your queries. So, either me or the TAs who are associated with this course will be answering all those questions. Okay, so, let us start without any further delay. Before we begin our lecture, before we begin our discussion on the kinetic theory, that is where we will start. I would like to revisit some of the very basics or very preliminaries of the thermal physics. Okay. So, let me start with the definition of a mole. Now, what is a mole? Now, in chemistry and physics, when we are talking about a mole, this is actually the quantity of matter that contains exactly the number of objects equal to the number of atoms in 12 grams of pure carbon. That is the definition of a mole. Now, what is an object? Object could be anything, object could be atom, object could be molecule, object could be ions, or object could be formula weight, depending on which system we are talking about. Next comes the definition of Avogadro number, the exact number of objects present in 1 mole of matter. In the first definition, we say that the number of object that is equal the number of atoms in 12 grams of pure carbon is 1 mole. But what is that number? That number is Na, the Avogadro number, which is given by 6.023 into 10 to the power 23 per mole, or we can also write it as mole inverse. Instead of writing it like this, we can write, we can write this as mole inverse, right. Now, Avogadro number is not a pure number, as we might see. This is the number of atoms or molecules or ions per mole. So, there is an unit associated with it. So, let us take an example. 1 mole of ammonia is Na numbers of has Na numbers of molecules, and if we talk about 1 moles of NaCl, it has Na formula weight of NaCl present in that. Similarly, if we talk about 1 mole of helium gas, it will be exactly Na number of atoms in that gas assembly, because we know that helium is a monoatomic gas, right. Next, the third definition is the definition of molar mass. What is that? So, we are talking about the number of moles, we are talking about the Avogadro number, which is the number that is present in 1 mole, and then the molar mass, that is the mass of 1 mole of substance. Now, mass of 1 mole of substance means, for example, if we have 1 mole of hydrogen, this is 1 gram of hydrogen, 1 mole of carbon is 1 mole of 12 grams of carbon, because 12 grams of carbon, 12 gram makes 1 mole for carbon, right. Now, that is written as capital M, and if the small m small m is the object mass, if that is the case, then capital M is equal to small m times Na, where Na is the Avogadro number. Okay. Now, I am pretty sure that you are all familiar with this definition, but I thought I would anyway recap this, because sometimes it is sometimes we mix up the definitions and we, while solving problems, we find it difficult. Next is the ideal gas laws. Okay. So, what do you mean by ideal gas laws? We have the Boyle's law, which says for constant temperature, the pressure of a gas is inversely proportional to its volume. Similarly, there is Charles's law that says for constant pressure system, the volume is proportional to its temperature. And then there is Gay-Lussac's law, which says the pressure is proportional to temperature, where the volume is fixed. So, pressure P remains, P is the notification, P denotes the pressure, T denotes the temperature and V denotes the volume of the gas assembly. Now, interesting point to note is that all these three laws are actually empirical laws. What do you mean by empirical laws? So, these are based on observation. So, we have a system or we have, or not we should say, the scientists have measured, performed different measurements on gas assembly, the pressure and volume relation, volume and temperature relation, pressure and temperature relation on certain certain gas assembly, and found that these laws are mostly valid. Okay. So, that is why these are called empirical laws. And why these are called ideal gas laws? Because it has been found that these laws are valid for most of the for gases with very low, under certain circumstances. So, we will come back to that, what are those circumstances, slowly and slowly we will go into that. But typically, let me tell you, when the pressure is low, the volume is large and the temperature is moderate, only when these laws are strictly valid. If we go to very low or very high temperature, or the pressure goes up or the volume becomes very small, then these empirical gas laws are not valid anymore. So, that is to say, there is a certain range of pressure and temperature in which these laws are valid for in general for a gas assembly. Okay. So, then what was done, that these three laws are there. Now, let us assume a situation in which pressure, temperature, volume, these three parameters in a gas assembly are all changing together. Then combining these three laws, we get that something called the ideal gas law. Now, what is ideal gas law? Ideal gas law is that PV, the product PV is proportional to T when all P, B and T are varying together. Now, the proportionality constant, once again measured experimentally, is N kBT, where N is the number of gas molecules. It was found out that N is the number of gas molecules and Kb is the Boltzmann constant. Now, combining, we have PV proportional to T with this proportionality constant of N kBT. So, we can write PV equal to N kBT. Now, instead of N, we can write N by Na times Na into kBT. Now, this N by Na, this one, this quantity N by Na is nothing but the number of moles of the system, and Na times Kb is nothing but another constant, because Na is a constant, Kb is a constant, that is also a constant R, the product. So, we get the celebrated ideal gas law, which is PV equal to nRT or PV equal to capital N KT. Once again, there are scopes of confusion. I also sometimes get confused between these two forms, which one is what. Please remember, when it is Kb, then it is the number of molecules. So, it has become a molecular level law, and when it is R, then we have number of moles. So, for 1 mole of gas, it will be simply PV equal to RT. Okay. So, the values of N, once again the value of this gas constant R is given by Na times Kb, which is 6.023 into 10 to the power 23 multiplied by 1.3 380648 into 10 to the power minus 23, which is the value of Boltzmann constant, and altogether we get a value of R is equal to 8.314 joules per calorie inverse per mole inverse, which is the universal gas constant. Okay. Fantastic. Now that we have this ideal gas law, which is P v equal to nRT, small nRT, this is, as we all know from our textbooks, school level textbooks, that this is the ideal gas law. Once again, let me point it out that at this point the ideal gas law remains completely phenomenological in nature, or the empirical in nature. Okay, not phenomenological, sorry, empirical in nature. That means these are based on observation. Okay. Now, is there any way by which we can prove the ideal gas law from pure theoretical point of view? That is the question that we have in mind. The answer is yes. When we use the kinetic theory of gases, we can actually prove this set of laws from, or not only the ideal gas law, but all three Charles's law, Boyle's law and Gay-Lussac's law from very fundamental consideration, fundamental physics of the problem, physics of the system. Okay. So, that is how. So, what is kinetic theory? Kinetic theory is a theory built on the microscopic picture of an ideal gas assembly that leads to gas laws. Not only gas laws, we will see that it will lead to pressure expression and mean free path and many other important parameters, but most importantly that this is a microscopic picture. It is not a macroscopic picture. Pressure, volume, temperature, all this quantity, they are macroscopically measured quantity. So, pressure, volume, temperature and n, small n, which is number of mole, these are all macroscopically measured quantity. But in kinetic theory, we will have microscopic picture, which will be I will be discussing very soon, and we will see that this microscopic picture is good enough to explain all these empirical laws. Okay. So, without further delay, let us start with the basic postulates of kinetic theory. Now, in certain books you will find there are 5 points, in certain book you will find that there are 8 points or on basic postulates, some books they use 7 points. It is more or less the same thing actually, but I mean I am not very strict about the number of points that we must have, but what is important is we need to have the few basic things which I am going to discuss now embedded in this set of postulates. First of all, that the gas assembly should contain a large number of identical molecules. What do you mean by large? Large means the number should be of the order of N A, the Avogadro number, and the basic assumption that we have that these molecules are like Herd spheres. So, we do not consider the shape of individual molecules, like we might have a tetrahedron shape, we can have a biradical diatomic molecule, triatomic molecule. No, we just consider that these are Herd sphere. Then these gas molecules, they are executing constant random motion, just so that means all the molecules are moving in all random directions such that there is no preferred orientation or preferred direction in the system. So, all the directions are equally probable. So, they are executing random motion in all possible directions. During this random motion, they are colliding with each other, they are colliding with the container wall, and all these collisions are elastic in nature. Okay. Now, also what do you mean by elastic? Elastic means they do not lose any energy because of these collisions. Okay. Now, the total kinetic energy of the molecules, because they are the collisions are elastic in nature, they remain constant unless there is some outside interference with the gas assembly. Also, the molecules do not have any other attractive or repulsive forces between each other, and another important point is if we consider the total volume of the molecule. For example, each molecule has a tiny volume, whatever it is, the atomic volume. If we combine all this volume together, then also the volume of the, this volume is very small compared to the total volume of the gas assembly. That means, we have a container inside which the gas molecules reside with a volume V, and let us assume this all the atomic volumes combined together gives you small v. So, small v is much less than capital V, or rather capital small v by capital V is much less than 1. Also, the last but not the least, gravitational attraction has no role to play here. Gravitational attraction or gravitational forces on these molecules are so tiny as compared to other effects that we can altogether neglect it. Okay, so, you can always find this postulate in many different, as I said, you can find it in many different forms, in many different books. You can find it also in the internet. We have chemistry liver text site, we have Wikipedia site. Everywhere it is stated in a slightly different manner, but these are more or less the basic points which the postulates must cover in order to have a completeness in the system. Right. Now, let us look into it in a slightly more pictorial way. So, let us first assume this picture in the left. We have a x, y, z coordinate, which is the standard Cartesian coordinate, and we have assumed a volume V. Okay, I should write V here. We have assumed a volume V, and we have a total number of capital N gas molecule present in this volume. Now, let us assume that there is a tiny volume dV present here, which is at some location we do not know, but let us in some location in this container. And let me tell you one thing, the shape of this container is not important. What is important is the total volume. Okay? And let us assume that there is a small volume dV that contains a small number dNV, okay, of this molecule. Now, the outcome of this, or from the postulate we can conclude that the density of this gas assembly remains constant, okay, because all the directions are equally probable and there is no velocity or temperature or pressure gradient inside the system. These are all written in this postulate. So, basically the system is in total chemical, thermal, mechanical, thermal and chemical equilibrium with the surrounding. What are these terms? I will explain once again when we will be discussing classical thermodynamics. But let me tell you, once this happens, the density remains constant. That means, N by V is equal to dNV by dV. And let us assume that dNc is the total number of molecules in this entire gas assembly between speed c to c plus dc. It is also assumed constant, and our okay, of course, depending on the value of c itself, but once we fix c, if we are looking to find out the number of molecules present between in the vicinity of a fixed speed value c, then this is also a constant. Okay. So, now this is our picture A on the left hand side. Now, we represent the same thing in a slightly different manner. We now switch to the velocity coordinate. What do you mean by velocity coordinate? Velocity coordinate means we have instead of x, y and z Cartesian axis, we map velocity of each of these particles in the 3-dimensional velocity space when we have Vx, Vy and Vz axis. So, I have just drawn 1/8 of the total space basically, or so, and please remember that velocity could be in any direction. So, we can have velocity components in all these 8 quadrant of this coordinate system, or I do not know what should I call it, no, not quadrant, 4, 5, yeah. So, I hope you understand. So, each half of this coordinate system will contain some of these molecules, because it is a velocity space. Velocity is a vector. We have just drawn the positive part Vx, Vy and Vz. So, each molecule from here will have a direct representation in this, I mean in this entire space, but we are just looking at the positive part of it, where Vx, Vy, Vz all positive. Okay. So, a molecule with all three positive with a velocity or rather with a speed c, for which all three of Vx, Vy and Vz are positive, will be represented by a point here. If for example, Vy is negative, then it will be in the neighboring coordinate of the coordinate system, neighboring compartment of the coordinate system. Okay. So, in this representation, if we once again point out that there is a element, this is given by dVx, dVx, dVy, dVz. So, this is the volume element in this velocity space. Now, let us assume that we are talking about a fixed speed c. So, that means we first make c constant, but of course, you have to understand that many combination of the velocity many combination of the x, y, z velocity components can produce the same value of c. So, it is not only, this equation actually does not identify Vx, Vy, Vz uniquely, but it actually acts as a constraint equation, okay, in this three dimensional space. So, we have one constraint equation, and the probability that a molecule selected at random has an x component of velocity between Vx and Vx plus dVx is proportional to dVx and function of Vx. Why proportional to dVx? Because if we enhance the range of the velocity distribution, velocity distribution width, of course, we will have more number of molecules. And of course, this the probability we are talking about, that a molecule has a x component of velocity between Vx and Vx plus dVx will be a function of Vx itself. Depending on whether the value of Vx is very small or very large, the probability might vary. Okay. So, we can write this in a mathematical form as, where is it? Right. dnVx. dnVx is the probability of finding a molecule with a velocity component between Vx and dVx, that is n times, n being the total number of molecules, some function f Vx times dVx. dVx is the interval in which, this is the allowed interval in which the velocity might, x component of velocity might lie. Now, let us go back to the postulates. We say that all three directions are equally probable. So, that is to say, there is no preferred direction in this gas assembly. So, if this is the rule for x direction, the same rule should apply for y and z directions as well, right. So, we can write two equations. Once again, we have two other relation, that identical relation for dn Vy and dn Vz as well. So, combining this, we can say that the total number of particles in the elemental volume with speed between c plus c and c plus dc, that is to say, in that elemental volume, to have elemental volume in the velocity space, of course, this space, to have velocity components between x, Vx and Vx plus dVx, Vy and Vy and dVy, Vz and Vz plus dVz is n times f of Vx, f of Vy, f of Vz times dVx, dVy, dVz, right. And if I now just bring this volume, elemental volume in the denominator, what do we get? We get the density of molecules with speed lying between c to c plus dc. And as we have already said, once we fix the value of c, rho c is a constant. So, next so immediately we get a second equation that says rho is equal to n times f v x, f v y, f v z, which is equal to a constant. So, we have two equations. One equation is this constraint equation, which tells us that two of this v x, v y and v z can be chosen independently, because they are related by one constraint equation. So, please remember, I mean, plus try to recall your classical mechanics text or your mathematical methods wherever you have encountered this. You have constraint equation, you have n number of independent coordinates and k number of constraint equations. So, the total number of independent coordinate is n minus k simply. So, here we have three numbers of independent three numbers of independent variables and one constraint equation. So, we have essentially two independent variables. Which of these two are independent? We do not know. So, in order to find out, or rather we in order to overcome this problem, what do? We first take the derivative of the first relation, take the derivative of the second relation and rearrange slightly, and we get these two differential forms. One is this one v x dx, v y dy. Oh, sorry, I should write v x. Okay, so there is a mistake in this relation. Let me correct it for you. First of all, this is not dx, dy, dz, but these are v x. Okay, sorry, v x, v y, v z, and in here there should be dvx, dvy, dvz. I will have to remove this relation altogether. Right. So, let us do it quickly. Yeah. F prime v x, f v x, dvx plus f prime v y, f v y, dvy plus f prime, oops, sorry, f prime v z, f v z, d v z. Sorry, this is not complete yet. Just have to write equal to 0. So, this is my fourth relation. Now, we have relation 3 and 4, and what we can do is we can eliminate this. So, as we have already said, there is a one of this two of this v x, v y and v z, they are independent, and we have these two relations. Now, how to make this relation independent of each other? I mean, these three coefficients independent of each other, coefficient of dvx, dvy, dvz, and equate them equal to 0 individually, we will see in the next lecture. Thank you.